let's have a look how to arrange the electron in ion system. For example, we already learned this in our secondary school. Therefore, ion system, we will have 2A14 2. This is the arrangement where this 2A for the first shell, and then 8 for second shell, 14 will occupy the third shell, and the remaining 2 will be put in the fourth shell. Try to count it back. 8 to 10, 10 to 24, yeah, 26. However, and later on, we try to arrange this one in electron configuration like this. So the first shell is 1s2, 2s2, 2p6, and then 3s2, 3p6, 4s2, 3d6, and then 4s2, and then this one is 4s2. So we can configure it like this. So we need to use this table or this rule to arrange our electron, where this one is showing the lowest energy that electron can occupy at a certain time and certain level. So like this, so the energy of this level have been determined by using quantum theory. That's why we will have this table. This is the simplification of this one that have been determined by using quantum theory. So here is how I use the knowledge of the theory here to determine the orbital or electron configuration for my system or my enzyme that I had been studying. So you can refer to this journal and try to get this journal to have a more understanding or more information regarding this configuration. So for example, if we have neon, and we have a 10 electron, so we know that in this one is one of the inert gas. So in our second level, we use 2A to represent the configuration of this neon, this atom. So 2 for, we'll be looking at the first shell, and the remaining will be given to the second shell. And later on, if we want to write in this way, what we need to do is we need to use this table. So 1s2, 2s2, and 2p6. Here is the rule. The s can hold up to 2 electron, p orbital can hold up to 6 electron, and d can hold up until 10 electron. So if we decide, we also can rewrite this one to this configuration or this form. So still 1s2, 2s2, 2p6. So here is the configuration for fluorine. So you can do it by yourself, how to arrange that. And for each of all the metal or the element in the table, we can arrange it into the electron configuration. So here is the proper way how. Here is the example of a few metal that I chose from the periodic table. So here, so you can try by yourself to arrange the metal ion So later on, if you remember that SPDF that we do it before, 1s2, 2s2, 2p6, and this kind of thing. SPDF, this is being determined using content theory and predict all of the behavior of the shape by using the quantum theory. So here is a few probability function. So if you refer to textbook or any quantum theory books, so they will have this kind of probability function. So it means that this is being determined probabilistically by the mathematical equation based on the quantum theory model. So later on, all the electrons in the atom have all systems have their own electron configuration, and each atom have a distinct fingerprint. So I can show you here. So this is the hydrogen, helium, sodium, calcium, barium, strontium, and so on, and the list will go on. So here is the the fingerprint of the electron. You can refer to it in the emission spectra, because because of light only come off at a very specific wavelength and it have frequency or energy. So if we look at the hydrogen is consisting of one electron and one proton, and this electron can emit several wavelengths, and it happened to all of the other atom. So where all of the other atom, for example helium, sodium, calcium, they contain more than one electron and one proton. So they can consist of several emission spectra. So by using this emission spectra, we can determine the kind of electron that have in our system. So this is the basic thing of a spectroscopy method. So as for GCMS, RCMS, this one is a basic concept of all the spectrum method that we will learn later. So we don't have a question how comes I have never seen a photon. Is because the length of the photon is too small. That's why we can't see it. But however, we can't see it. However, we can sense it. For example, in a sunny day, and we can feel when our body touch the light, and then we can sense the energy like hot. So we do have a few example here. So where for the light, here is the photon that it contains for every light here, such as in sunny day, moonlight, moonless night, light from the most naked star. So here is we can't see, but the photon is there. So I already covered it before here, all the quantum here. So for typical quantum object, the electron is very, very small. That's why we are not able to use classical mechanics to explain quantum behavior. So here is a double slit experiment. The experiment is actually used to determine the properties of particles. So that's why for the double slit experiment we can settle that all particle or small particle can have a particle with duality or particle with properties. So all the small particle will have these two properties, particle and wave at the same time. And then the hydrogen atom. So we know that the hydrogen atom consists of one electron. Hydrogen consists of one electron, and for the ionization energy we can remove this electron by using the quantum function, and then to remove this electron completely from the system is the energy needed is 13.6 eV electron volt. And then to remove any kind of atom, any electron in the atom, so we have this formula Z squared times 13.6 eV, where Z is the number of electron. So this is the formula for energy of ionization energy if we want to remove the electron completely in any atom. So all of this formula is determined by using a quantum theory, and again it involves with a complex mathematical derivation, so I will not explain to you. So it just enough for you just to know this theory or this formula. And thank you. So if you have any question, please let me know. And for the part 2, you can refer to GHOST, where Dr. Zamir, the video or the explanation for Dr. Zamir, I think is good enough for you to understand for the quantum theory for part 2. Thank you and have a nice day.